Hey guys, I'm Bill. In this tutorial, we're gonna talk about a more straightforward way of calculating the outputs of a neural network. Why do you want a straightforward way? Because in the last tutorial we talked about one way, which is to multiply the activation by the weight and add in the bias for every single neuron in the neural network, which is very inefficient for a computer, because remember, we're running these on a computer and we want a more efficient, simpler way. And there's actually a way that is really simple, and it only involves some simple arithmetic and absolutely no complex keeping track of connections between neurons, these kind of heavy lifting for computers. Let's get started. Before we can talk about this new way of calculating outputs, we need to know what are vectors and matrices. Let's get started with vectors. Vectors are just directions. You can see we represent vectors with I can draw a better vertical line there. Yes. And we represent a vector like this, and we can put numbers inside of it. For example, I can make a vector of 1, 2, 3, 4. It's really just a list of numbers if you see it that way. But there's actually a special name for every single length of a vector. For example, if there's 2 elements in a vector, then we call this a 2-dimensional vector. And if it has 3 elements in it, we call this a 3-dimensional vector. You may be wondering why we call that x-dimensional vectors. That is actually because, as I said earlier, vectors represent the direction. For example, if I have a vector of 3 and 4, if we draw an xy coordinate here, 3 will be, I guess, somewhere here, and 4 will be somewhere here. And then we can draw a point here, and if we drag a line from this center point to this point right here, this is a direction. It's a direction that points this way. And so we call it 2-dimensional vectors because xy coordinates are 2-dimensional, right? It has an x dimension and a y dimension. And if you add another value in the vector, it will become a 3-dimensional vector because a new dimension called, I guess, commonly z will be added here. And because of that, we call it 3-dimensional. And we live in a 3-dimensional world, right? So I'm gonna get rid of this. You can just remember vectors as directions or a list of numbers, whichever one you like. Next, what I want to talk about is matrices. Matrices are interesting because I'm gonna draw out a very simple matrix here, like so. Just randomly placing values into it. It may seem very familiar because matrices are actually just multiple vectors if you think about it. You see, this you can say that it's a vector, and this you can also say it's a vector because there's 2 values with a direction like that. And that's actually the only thing that you need to worry about. Matrices are just, you can think about it as a grid of numbers. This is a list of numbers. This is a grid of numbers. It's 2-dimensional. And the dimensional that I mentioned here is different from the dimensional that I mentioned earlier because they're different things. In this case, there's actually 2 dimensions to this, little grid thing. right? So now I want to talk about a little bit of arithmetic with these types of stuff. For example, what if we want to multiply a vector, for example this vector, by say x? The answer is we just multiply it element-wise like this. It will be equal to 3x, a vector of 3x and 4x. We just multiply this single variable here by every single thing inside of the vector, and we'll get this. And what if we want to multiply matrices? Well, that is very simple too. If we want to multiply by a single number, then we'll just get 1x, 3x, 4x, and 2x. Very simple so far. But what if, I'm just gonna remove everything now here. What if we want to multiply it by another vector? What if we want to multiply a vector by another vector? Well, there's actually two ways to do multiplication in vectors. One way, this is actually not the one used very often, is that we just take everything inside the second vector, and multiply every corresponding element with each other. So, for example, this is actually called the Hadamard product, or element-wise product, and we represent it by a little circle, and you do something like that, and then what you're gonna get is 12, because 3 corresponds to 4, and 20, because 4 corresponds to 5. But this is not the one that we're going to use for this new method of calculating the outputs of a neural network. What we're going to use is something called the dot product. The dot product is really simple too, but there's a little catch. The number of rows in one vector will have to be the same with the number of columns in another vector. And I didn't mention that, but you can write it, like this, horizontally. You can do it whichever direction you like. And how do you calculate this? Well, it's very simple. We just multiply each of, for example, in this thingy, the first element is 3, the second element is 4. In this one, the first element is 4, the second element is 5. We multiply each of these corresponding elements, and then we add it together. Let me show you that. This is going to be equal to, so I want to get us a little more space here, so I'm going to do that. This is going to be 3 times 4 plus 4 times 5, which is equal to 12 plus 20, which is equal to 32. And so, if we multiply this vector by this vector, we're going to get 32. And now that we've covered how to multiply vectors by vectors, let's think about how we can multiply matrices by matrices. I'm going to draw another matrix here. For example, I'm going to write it as x, y, a, and b. This is just random. And then, how are we going to do this? The amazing thing is, first of all, I just want to get through this. As with the vectors, when you multiply two matrices, one of the number of columns in one of the matrix and the number of rows in the other matrix has to be the same for this to work. If it's not the same, it's gonna come out with a lot of problems. I'm not gonna get into the details for now. Maybe later. The way we're gonna do this, we're gonna take the first row of one matrix, and we're gonna take the another column from the other matrix. And you can see that there's two rows in the first matrix and two columns in the second matrix. And what we're gonna do is, for example, this is the first row, this is the second row. We're gonna multiply, we're gonna dot product each of these little chunks together, right? And there's a special order to this. You're gonna first take the first row of one of the matrix and dot product it, like we did it here, with another column in the other matrix. And then we're gonna take the first row from one of the matrix again, and then dot product it with the second column of the other matrix. And then, now that we've run out of columns, we're gonna continue to this thing right over the second row of the one of the matrix, and dot product it with the first column of this other matrix, and then we're just gonna repeat it. So it's basically just, we're gonna first dot product this with this, and then this again with this, and then we're gonna dot product this with this, and then this with this. Let's try it out. First, what we're gonna do is we're gonna create another matrix, and then we're gonna do the exact same thing that we did here, but we're gonna do it with every combination. And let's try it out. So 1x plus 3x, and then this right here will be 1y plus 3, running out of space already. Let's just expand it to here. So 1x plus 3x, oh no, 3a, and then 1y plus 3b, and then 4x plus 2a, and then it's gonna be 4y plus 2b. This will be the result of this will be the dot product between this matrix and this matrix. So let's summarize here, because there was a lot to take in. We're going to take one of the matrix, and for each row, we're going to multiply, we're going to take the dot product of that with each of the columns in the other matrix. And we're going to repeat the same thing with the next row, and the next row, and the next row. And you can see there's a very special way to write the new matrix. It's just, it's it's very intuitive actually. When you multiply this by this, you're going to put it in the first place here. When you multiply this by this, we're going to put it here. Basically, when you multiply the dot product, the new position of that dot product will be the row index in the first matrix, comma, the column index in the next matrix. For example, if we take this for example, we're multiplying, now we're taking the dot product of the first row and the second column, and because of that, it's in the first row and in the second column of the new matrix. Now that we've got that out of the way, we can start to talk about the new method for calculating the outputs of neural networks. I'm going to drag it over here. You can see that I have drawn a very large neural network compared to last time. And what we're going to do is we're going to, if you still remember, each of these layers, each of these neurons represent a number, an activation, right? And what we're going to do is we're going to organize each of these activations inside of a vector, which is a list of numbers or direction, if you remember. And we can write it as something like this: the activation of the first neuron in the first layer, and the second element will be the activation of the second neuron in the first layer. This will be the activations for the first layer. We don't really need this visual representation of this first layer now. We can just transform it into a list of numbers. And then for these weights, just still remember that we index this in a very strange way, which is we first write W and then we write the end of the connection and then the start of the connection and then the layer. The end and the start seem to be in the opposite, is written in the opposite way, right? But it's actually not if you write it as a matrix. If you write it as a matrix, you're going to have W1, the first neuron, to the first neuron of the first layer, and this way belongs to the second layer. And let me just write it out here. The first neuron in the second layer to the second neuron to the first layer, and 2, and then W2, 1, 2, and W2, 2, 2. And now you can see that even though this seems a little weird at first, you'll notice that these two numbers perfectly align with how we index matrices. For example, this weight is in the first row and the first column. This weight is in the first row and in the second column. This weight is in the second row and the first column, and so on. So it really lines up if you think about it in a matrix standpoint. And now we can represent all of these other ones as matrices or vectors too. And we're going to do that. Oops. We can do that. So close. This is so close. Yes. We can represent this one as A1, 2 and A2, 2. And then don't forget the bias. Each of these neurons also have a bias. We're going to write it as, nope. Just draw a straight line here. Yes, that is better. Yes, that is way better. Okay. This is going to be the bias of the first neuron of the second layer and the bias of the second neuron of the second layer. And we can then represent these two connections as a matrix. So W the first neuron of the third layer to the first neuron of the second layer, and this belongs to the third layer, and then W 1, 2, 3. And finally, for this little neuron right here, we can represent it as just a one element vector, and it's gonna be A1 of the third layer, and the bias is gonna be B1 of the third layer. And now that we've represented all of these, all of the neural network as vectors and matrices, we don't really need the neural network anymore, but we're going to leave that there. And now that we've represented all of these as vectors and matrices, we can finally calculate the output more easily. For example, if we wanted to calculate the activations of this whole layer here, what we can do is we can multiply A11, A21, which is this vector right here, with the weight matrix. I'm just gonna quickly write it down here. And 212 W222. And then if we add the bias, I'm really just copying these three right here, so you can just you don't need to worry, this is not anything new. Okay, now if we want to get the result, well, the resulting vector will actually be the activations of the second layer. Yeah, super duper cool. If you calculate all of this, it's going to result in the activation of the second layer. Well, let's see how it's done. If we first do this part, just this part right here, the resulting matrix will be, we're going to take each of the rows of this second matrix here and multiply all of the combinations for each of these elements to the first matrix. It's a handful of stuff to say, so let's just do it. Well, first, we're going to multiply this weight by this activation. 112 and A11. And also W. Also, then after multiplying this thing, we also need to multiply the second weight here by this activation. So W12 to A21. And then we need to multiply the next row with this column here, and we'll get W212 and A11, and then W222 A21. This is the matrix that we'll get. And then you can see that we're basically just multiplying each of these weights with each of these activations. Yes, we're multiplying. First of all, we're multiplying this weight by this activation, and then we're multiplying this weight with this activation, and then we're multiplying this weight, this weight right over here, and multiplying with the first activation of the first layer, and then we're multiplying the weight, this weight, 2 to 2, of the second layer with this activation. And you can see that this part right over here, forgot the plus sign, yes, and then you can see that this part right over here is basically just the activation of this neuron, because we're multiplying this weight by this activation and adding it to the product of this weight and this activation, and these two are the connected weights and activations. So this is actually correct. This is the activation for this neuron, and this is the activation for this neuron. But if you didn't forget about it, there's also the weight that we need to take care about. And the weight is very straightforward too. If you think about it, you can see that we're just adding it. So we're just gonna add it in there, like so. And then we are done. Yay! And now finally, before you forget about it, we also need to squash the whole thing down with an activation function. And we're going to use a sigmoid. Yes. This whole expression here is basically the activation of the second layer. And now what we can do is we can repeat the whole step. Oh, wait a second. We need to add this equal sign here. Then we need to repeat this whole step with the second layer and the third layer. So what we're going to do is we're going to then multiply this whole expression with this weight, right? The weights connecting the second layer with the third layer, and then we're going to add the biases of the second layer and the third layer, and then we'll get the final output. And today I just want to finish all the steps, so let's get to it. So we're gonna take this whole expression now. And take this whole expression. Very inefficient way to copy a matrix. Yeah, I'm just gonna refer to it as the vector. And then we're going to multiply this vector by this vector, another vector. Or this is, actually you can consider this as a matrix too. Vectors are just very small matrices. Matrices. And then we'll add the bias. And there we go. So this whole expression that I wrote here is gonna be the activation of the last layer here. And the only thing that we need to do is that we need to plug this whole expression into here. And we have officially finished calculating the outputs. That was straightforward. Because if we use this method, why is it efficient? Because we don't need to record all of these connections. We just need to store all of these matrices and vectors of weights and biases and activations, and then we can just multiply it, add it together, and then we'll get the result. And that is a great thing about these efficient ways. It's not complicated. That is the only difference between that and the methods that we learned about in the last tutorial. So thank you guys for watching. If you like this video, please like it, click on the thumbs up, and then don't forget to subscribe, and don't forget to check out my website at www.whatyoudid.com, and have a great one.